Instead of having one long video dragging you through step by step, component by component analysis of a refrigeration cycle, what I'm going to try to do is bust these videos up into component by component by component to try to keep it as simple as possible, and also to help you see how this is a review of material that you've already covered. So what I want to do in this video is go and look at the compressor part of the refrigeration cycle. So remember, we've got compressor, condenser, expansion valve, and evaporator. So let's focus this time analyzing the compressor, because typically that's where you start in your refrigeration cycle analysis, is at the inlet of the compressor. Okay, so let's look at our basic sketch, our basic layout. We're going to focus totally on the compressor, inlet state 1 and outlet state 2. And of course, we see a rotating shaft driving the compressor. An electric motor is driving the compressor, so W dot is involved. What's that going to look like on our temperature entropy diagram for the ideal cycle, for the reversible and adiabatic compressor? Now, under all circumstances, we're going to consider the compressor process to be fully insulated. But let's take another step and say that for this analysis, our compressor is reversible as well as adiabatic. In other words, isentropic. And so this screenshot right out of your textbook, we come into, let's see, what are we doing? We're coming in as saturated vapor, coming out of the evaporator as saturated vapor at state 1, into the compressor, and leaving at the same entropy. Textbook calls it 2S, and I call it 2I for isentropic. Well, what is a air conditioner compressor going to look like anyway? What I've tried to do is, this is an example of what's called a scroll compressor. And so proportionally, the compressor part of this unit is not a whole big part. That by far and away, the biggest part of this enclosed unit is the electric motor drive. Here, this is going to be our inlet. Saturated vapor refrigerant is going into the scroll compressor here, compressed reversibly and adiabatically. So that, therefore, I think we can visualize in our heads with the TS diagram and the vapor dome. We can say, sure enough, it's going to be superheated vapor refrigerant coming out at a much higher pressure. So this is basically what a scroll compressor looks like for refrigerant. What does the compressor look like for a refrigerator? Well, if you pull your refrigerator out in the middle of the floor and look back behind it, you're going to see the compressor down low, okay, and probably in a little it's going to be connected or bolted to the base of the refrigerator, and there probably will be some rubber vibration isolation feet underneath that compressor. But here's basically what it looks like. The top part, you can see there's the compressor part. The bottom part, the electric motor drive, is down below. And so, and they run pretty quiet, right? What does the compressor look like for an automotive air conditioning system? Well, you pop open the hood and you're going to see, this looks like this is the alternator, isn't it? This is the compressor part that for your automotive. You can see that it's a belt drive basically from your crankshaft of your engine. That's what's providing the power to run the compressor. And so there's the compressor underneath your hood for your automotive air conditioning system. Okay, and let's see. Yep, and I see here, as I look at the labels here on this cutaway view, I see that this would be considered a scroll compressor as well. Not positive displacement, but a scroll compressor. what is your sketch going to look like? And so, of course, you're going to be drawing a sketch that looks very similar to what's in the textbook. But if we just focus on the compressor alone, what does your compressor sketch look like? Well, I've just taken a screenshot right out of the book. Tried to add a few labels. Let's look at W dot. Well, remember W dot typically, when we just say plain old W dot, we should say W dot out. And here I'm labeling my sketch W dot out is less than zero because it takes power to drive the compressor. In my world, I never label a sketch W dot in. Um, Now, that can certainly be done, but I'll tell you, when I try doing it, I get totally confused and I don't stick with the fundamentals. So I always go with W dot out, but I'm careful to label it less than zero. How about Q dot, heat transfer? I am labeling Q dot in equals zero. It's an adiabatic compressor. So on my sketch, I am going to put that. There's no heat transfer. It's adiabatic. I've said open system. Yeah, there's mass flow in and out. It's steady state, steady flow, and there's one inlet and one outlet. So I just label a single M dot. And I remind myself to get even with the book, little w out, little w is equal to W dot divided by M dot. And that's a big reminder for me because typically a lot of practicing engineers and instructors will call little w the work of the control volume. And recognize that the units of little w for this open system are kilojoules per kilogram, little w, kilojoules per kilogram, but it's really power divided by mass flow rate. And so to stay consistent with the book, the first law for our compressor, we're going to recognize we don't have any changes in potential energy. We've got negligible changes in kinetic energy, so we're going to set those both equal to zero. And so very quickly, we can plop down the first law for steady state, steady flow, one inlet, one outlet, delta KE, delta PE 0, Q in, well, that's going to be 0 for our compressor. I'll strike that out. Minus W out is H2 minus H1, or in other words, W out is H1 minus H2. That's going to be less than 0. Let's go a little further, okay? And so let's look at so that covered the isentropic compressor. No, it covers both situations. But is our compressor isentropic, reversible adiabatic, or is it adiabatic and irreversible? Let's look at both of those cases. What if we have, on the left-hand side, what if we have a reversible and adiabatic compressor, isentropic? Well, state 2 is going to be, I call it 2I, book calls it 2S. Certainly, you're going to say numerically S2I exactly equals S1. Let's see, what would I do? I would look up S1 as S sub G at the pressure P1. So somehow I'm going to be able to determine what is S1 that equals S2. Typically in problem solving, you're going to know what the pressure is, the outlet pressure of the compressor is. So typically that's given. So let's see, how would I get the properties at state 2I or 2S? Well, I've got the entropy and I've got the pressure. I know my phase is going to be a superheated vapor. I can see that with my eyes. And so I would go and I would look up, say, the temperature 2I in the superheated tables, and I would need to interpolate to find that. Similarly, I also need to interpolate to find H2I, the enthalpy. So let's go back. Let's go back a slide. That's if my compressor is reversible and adiabatic, I need H2, don't I? I need H2I. Okay, back to the original slide. So yeah, how do I get H2I? That's how I would get it. I need two independent properties at state 2. Now, let's say, so we're going to do that under all circumstances. We've got a little bigger problem if we realize that our compressor is adiabatic but irreversible. So this is a reprise of chapter 6. Okay, so you see chapter 5 and 6, we're pretty good at studying the isentropic compressor. You have some experience studying the adiabatic and irreversible compressor, and that should immediately remind you, oh yeah, compressor efficiency. Typically, compressor efficiency is a known or given value. It could be typically 80 to 85% compressor efficiency. Well, how are you going to find state 2A, the actual outlet enthalpy? Now let's refresh our memory a little bit about what we did in chapter 6. The first thing we did was studied the isentropic compressor first. So we went through this analysis that we just talked about. Okay. And so we found W isentropic from the first law once we found H2S or H2 isentropic. So we find W isentropic first. The next thing we do is get W actual. Well, how do we get W actual? We remember the definition of compressor efficiency, and that's little W isentropic divided by a little W actual. Well, let's see. We just found W isentropic by analyzing the isentropic compressor. Typically, the compressor efficiency is a known or given value, so we find W actual as a numerical value. Then we go back to the first law. Let me go back a slide. We go back to the first law. Here it is. So W actual we would find and solve for H2 actual since we already know H1. So that's the way we're going to handle a compressor that's associated with a refrigeration cycle when we know that the compressor is adiabatic but irreversible, and typically the compressor efficiency is known or given. What does that look like on the temperature entropy diagram? So if we do have an adiabatic but irreversible compressor, put it all together. So here is our straight line for the isentropic situation. Remember, I call it 2I. Textbook calls it 2S. The dashed line is going off to the right. Entropy is increasing for this adiabatic compressor. The textbook calls it state 2. I call it state 2A for 2 actual. And so I hope that sketch, so looking at the sketch of the compressor process gives you a pretty good idea of how would I do the analysis for the compressor part of this refrigeration cycle. This is what your sketch should look like for the adiabatic and irreversible situation. You should see both of these lines, both the solid line for the isentropic, which you must study anyway, the dashed line for the irreversible adiabatic situation. Okay, so let's say, well, yeah, I think I get that. I remember doing things like that in chapter 4 and chapter 6. Yeah, I remember that. So I'm ready to start crunching numbers. So as a reminder, I've worked out from start to finish problem 10.4 that's going to incorporate the analysis of all the components. Go to Homework Solutions playlist and try this video, 35-minute video, problem 10.4 that's fully worked out. So what's our recap for this on terms of the compressor analysis part of a refrigeration cycle? It's a recap of chapters 4 and 6. You've got experience at that already. You're dealing with a phase change substance. In other words, for the compressor, you're looking at saturated vapor at the inlet, superheated vapor at the outlet. You've got an open system, steady state, steady flow, one inlet, one outlet. You have to decide from the words of the problem, is it isentropic, also called ideal? Ideal refrigeration cycle would be an isentropic compressor, or is there enough information given in the problem that says it's irreversible and adiabatic? In other words, is the compressor efficiency given? Your job is to determine the work, little w, which is W dot over M dot. And then once you've got W dot over M dot, that's when you'll then determine the outlet enthalpy for if you have the actual situation, the uh, ice, the adiabatic and irreversible situation. Okay, so that is a quick review of how would you analyze a compressor that involves a phase change substance, in this case, refrigerant, and how would you numerically determine the power required to drive the compressor, um, and or how would you get the actual outlet enthalpy? And you say, well, what? I don't care about the outlet enthalpy. You're going to need to care about it when you move to the next component, which is the condenser. So you have to have that outlet enthalpy of the compressor so you can do the thermodynamic analysis on the condenser. Hope that helps, and stay tuned for the condenser analysis.